The darkness comes first, not as a thing that swallows light, but as the absence of any place for light to be. There is no space yet, no fabric to stretch across, no direction to face. And then, without warning and without origin, the smallest conceivable speck of energy becomes everything. It swells not at the speed of light, but far faster, so fast that even light could never hope to cross the swelling field it leaves behind. This is inflation, a rapid, near-instantaneous expansion that smooths the newborn universe, ironing out any roughness, scattering any hint of structure into the uniformity of a perfect void. The entire process takes less time than it takes for light to cross a proton. In that fraction of a second, the universe grows from subatomic to macroscopic, and then keeps going effortlessly, surpassing the scale of entire galaxies, though no galaxies exist yet. Space itself is not moving through anything. It is the anything now, and it is growing. No boundary is pushed outward. There is only more of it arising everywhere at once. In this inflationary burst, quantum fluctuations, tiny random wrinkles at the smallest scales, are stretched to cosmic proportions. These wrinkles are not smoothed away but amplified. They will one day seed all structure, the vast web of galaxies, the empty gulfs between them, and the islands of matter where stars will burn. A microscopic uncertainty written into the laws of nature becomes the blueprint for everything. It is an irony of scale. The largest structures in the cosmos trace their origins to the smallest events imaginable. The gentle cluster of galaxies that will become the local group home to the Milky Way owes its existence to a fluctuation smaller than an atom. Inflation itself is a mystery, not for lack of equations, but for lack of confirmation. The theory explains much why the cosmos appears so uniform in all directions, why space is geometrically flat, why relics like magnetic monopoles seem absent. Yet no direct measurement has captured the precise signal. Inflation should leave behind a faint curl in the polarization of the cosmic microwave background. Astronomers look for it, still sweeping the sky for that delicate fingerprint in ancient light. If the inflationary moment were to play out in slow motion, the emptiness would not be silent. At those scales, energy itself is restless. The vacuum seethes with virtual particles flickering into being and vanishing again, a chaos smoothed into an even field by the furious stretch of space. The expansion is not into the dark, it is the dark, creating the very canvas on which any later light will shine. One might imagine it like the slow opening of a paper lantern, though here slow means impossibly fast and the lantern has no edges. The surface grows everywhere all at once, so that any 2 points are carried apart not by motion through space, but by the steady creation of more space between them. When inflation ends, the energy that drove it does not vanish. It converts into a sea of particles and radiation, a sudden flooding of the emptiness with substance. In moments, the universe is hot beyond comprehension. 1 trillion degrees, perhaps more, its particles colliding so often that no stable structure can form. This is the beginning of the hot Big Bang, the familiar era where matter and energy churn through the rules of physics we can test in laboratories. Only took 13.8 billion years for the evidence of this beginning to reach us. Only took a cosmic accident of expansion for our sky to hold the clues. And only took the smallest fluctuations imaginable to grow into the galaxies we see tonight. The fabric of space is still stretching now, but the way it stretches has changed. The furious pace of inflation has slowed to something far gentler, though by any human measure it remains vast. A galaxy, 1 billion light-years away, is carried farther at thousands of kilometers per second. In the deep future that will seem stillness compared to the memory of inflation's first breath. No one knows what powered that initial surge or what before could even mean. In the mathematics, inflation can be eternal in some regions, bubbling off new universes endlessly, while ours is merely one bubble among countless others. But this too remains unconfirmed, a speculation that fades into the edges of what can be tested. The evidence we have is here the smoothness of the cosmic microwave background, the flatness of the universe, the arrangement of galaxies across billions of light years. They point back to a moment when space itself was young and restless, stretching faster than any light could travel. It is easy to forget that the universe does not expand into something. There is no surrounding void waiting to be filled. The expansion is the growth of the very distance between things, a change in the metric of space, not a movement through pre-existing space. The irony is quiet and complete. The universe has no center yet. Everything is moving away from everything else. Every observer in every galaxy would see the same retreat. And so the first act of cosmic history is not an explosion, not a shattering, but an unrolling. An unrolling so complete that the distances between any 2 points stretch beyond communication before light has a chance to cross them. Whatever the universe contained before this moment is lost forever to the rest of it, separated not by walls, but by expansion itself. The calm that follows is deceptive. The next 380,000 years will be turbulent beyond anything the human mind can picture, the hot plasma of the early cosmos vibrating with energy, the seeds of structure waiting to emerge. But the foundation has been laid. The scale of the universe has been set beyond any earlier limit. The wrinkles in its smoothness have been placed, and space once nothing has become the stage on which all else will happen. Somewhere in that smooth-stretched expanse is the faint promise of every atom that will ever exist, every star that will shine, every planet that will orbit, every life that will think. It begins here with a breath in darkness, too brief to feel, too immense to measure without the patient work of billions of years. The light comes late. For hundreds of thousands of years after inflation ends, the universe is bright in temperature but not in sight. It is filled with a dense hot plasma of protons, electrons, and photons locked together in constant interaction. Photons cannot travel freely. They are scattered endlessly by charged particles ricocheting in all directions, unable to escape. In this early state, the cosmos is opaque, a fog of pure energy and matter. As the universe expands, it cools. Cooling is the quiet alchemy of cosmic time-space. Stretches, wavelengths lengthen, and the temperature falls. The collisions between particles grow less violent. The photons, still restless, feel the grip of electrons weaken. At roughly 380,000 years after the beginning, the cooling reaches a threshold. Electrons and protons, once kept apart by the sheer heat of the plasma, can at last combine into neutral hydrogen atoms. This moment recombination is the great release. Photons are no longer scattered by every encounter. They can stream through space without constant obstruction. For the first time, the universe becomes transparent. Light can travel unbroken, carrying with it the imprint of the conditions in which it was freed. That light is still here, still crossing the cosmos, though its journey has changed it. Stretched by the expansion of space over billions of years, it has shifted from brilliant visible wavelengths into the soft microwave glow of 7 kelvins above absolute zero. It is now the cosmic microwave background, the oldest light we can see, and the most ancient photograph in existence. In its subtle variations, it carries a map. The tiny temperature fluctuations, no greater than 1 part in 100,000, mark the seeds of future structure. Where the glow is a little warmer, matter was once a little denser, where cooler, a little thinner. From these faint ripples, galaxies will grow. There is a soft irony in how much is written into so little. The difference between a dense knot of matter and a nearly empty void is recorded in a whisper of warmth across a sky that appears uniform to the naked eye. To see the structure, we need instruments cooled nearly to absolute zero, tuned to the faintest of signals machines like Cobe Map and Planck. which have measured this background in exquisite detail. Yet for all its detail, the cosmic microwave background is not a complete story. It tells us about the universe as it was 380,000 years after the Big Bang, and only in projection like the surface of a sphere surrounding us in every direction. We cannot look beyond it with light. The photons from earlier times are trapped in the opaque plasma, their path forever blocked. To know what came before, astronomers turn to other messengers, neutrinos, gravitational waves, or the mathematics of theory. Here lies another quiet mystery. The patterns in the cosmic microwave background fit neatly with a universe composed mostly of ingredients we cannot see: dark matter, which pulls but does not shine, and dark energy which pushes without mass. The light we see, the stars, the galaxies, the nebulae accounts for less than 5% of the total cosmic content. The rest is invisible, yet shapes the universe's fate. It is easy to mistake this background light for something gentle, something dim and far away. But at its origin, it was as bright and intense as the surface of a star. Only through the patient work of expansion has it softened into its present form. It has crossed almost the entire age of the universe, cooling with every billion years, yet still carrying the signature of its birth. One might think of it as the afterglow of a lantern extinguished long ago, the glass now cold, the light dimmed to an ember, but still illuminating the shape of the space around it. The microwave background is not a remnant of a single flash, but the collective release of photons across the entire cosmos, at once all set free in the same brief moment. Only took the cooling of 380,000 years to turn the universe from fog to clarity. Only took the vastness of cosmic time to stretch that light into microwaves. Only took human ingenuity in the last fraction of that history to notice its presence at all. In its evenness, the background light is also a test. Inflation predicts that the universe should be smooth at the larger scales with tiny variations seeded by quantum fluctuations. The observations match this remarkably well, giving weight to the theory. Yet there are anomalies, slight asymmetries, unexpected alignments that do not entirely fit. Whether these are true cracks in our model or mere statistical quirks is still unknown. The cosmic microwave background is also a marker of distance in time. Anything we see beyond a certain redshift around 100 would have to pass through the opaque era before recombination, which no photon can do. This is the surface of last scattering, the furthest wall of light. Beyond it, the universe is invisible to our eyes, though not beyond reach for our mathematics. Astronomers often describe the background as a baby picture of the universe. The comparison works, though the timescale is misleading. By this stage, the cosmos is already hundreds of thousands of years old, yet it has not yet formed even the simplest of stars. The matter that will one day form galaxies is drifting in diffuse clouds, held together only by gravity's patient pull. The photons released at recombination travel in straight lines through space, but the space itself is not static. As the fabric stretches, their wavelengths lengthen, carrying the record of expansion within their color. This is redshift written on a universal scale. Every ancient photon bears the measure of the space it has crossed. If the background were visible to human eyes, the sky would be awash in soft light, the same in every direction. There would be no sense of up or down, no darker edges, no horizon. Just an endless, quiet brightness holding in its pattern the faint promise of all that will follow. The light we see today is not the same light that once illuminated the newborn universe, not in the sense of the same photons bouncing from surface to surface in a static room. These photons have travelled unbroken since their release, changing only because the stage on which they move has changed. That stage is larger now by a factor of over 1,000, and still the background light does not fade completely. It will remain long after the last star burns out, long after galaxies slip beyond visibility, long after even matter itself begins to decay. It is the first light we can see, and perhaps it will be the last to vanish. The cosmic microwave background is a reminder that the universe remembers its own beginnings in the quietest of ways, in patterns almost too subtle to notice, in temperatures barely above nothing, in a glow that is everywhere yet invisible without patient searching. And from that glow the story of expansion begins to take measurable shape. The galaxies come later drifting into view as if from a great distance, though they are not moving through space so much as space is growing around them. Gravity has been at work for hundreds of millions of years, coaxing matter together in the slight overdensities left from the early ripples. Hydrogen and helium, the simplest elements forged in the first minutes after the Big Bang, collapse into clouds, spinning slowly, falling inward under their own weight. The first stars form within these clouds, enormous and short-lived. They burn with a brilliance the universe has not seen before, flooding their surroundings with ultraviolet light. This radiation breaks apart the hydrogen fog between galaxies, reionizing the cosmos and making it transparent once more, not for photons from the cosmic microwave background which have long been free, but for the newborn starlight now beginning its own journey. These first stellar clusters gather into the earliest galaxies. They are small by the standards of today, a fraction of the Milky Way's mass, yet they are the seeds from which larger structures will grow. Mergers become the rule, not the exception. Small galaxies collide and merge into larger ones. Their stars are scattered into new orbits, their gas compressed into fresh bursts of star formation. Over billions of years, this quiet violence builds the grand spirals and massive ellipticals we see in the present-day universe, and yet from the moment they appear, galaxies are already drifting apart. The expansion of the universe does not pause for their assembly. On the largest scales, the distances between galaxy clusters increase with time, a steady stretching of the cosmic fabric. Inside clusters, gravity wins the galaxies there remain bound together, but between clusters expansion rules and the separation grows without end. This expansion is not something we can watch in real time with the naked eye. The changes are too slow for human senses, their pace measured in fractions of a percent per 100 million years. A galaxy 100 million light-years away is receding at hundreds or thousands of kilometers per second, yet its apparent size or position in the sky will not shift perceptibly in a lifetime. Still, the light carries the story. When astronomers split the light from a distant galaxy into its spectrum, they find its characteristic absorption line shifted toward the red, stretched to longer wavelengths. This redshift is not a Doppler effect in the usual sense. The galaxy is not moving through space away from us. Instead, the space between us and the galaxy has expanded during the light's journey, lengthening the light waves themselves. There is a quiet irony in how familiar this idea can seem when reduced to analogy, yet how alien it truly is. We say space stretches, but this stretching is not a force pulling on matter. It is the metric of the universe, the very definition of distance changing with time. In this framework, galaxies are mostly at rest with respect to their local surroundings. It is the scale of those surroundings that is increasing. Some galaxies do move through space in addition to being carried by expansion. The Milky Way, for instance, is on a slow collision course with Andromeda, the largest galaxy in our local group. In about 4 billion years, the two will merge into a single larger elliptical galaxy. Their mutual gravity overcomes the feeble push of expansion at such close range. But on scales beyond the local group, gravity's grip fades and expansion dominates. The result is a cosmic tapestry where the nearest galaxies may approach or drift sideways, but the more distant ones always recede. Beyond a certain scale, a few 100 million light-years, every galaxy moves away from every other, the pattern repeating no matter where the observer stands. There is no preferred vantage point, no central hub from which expansion radiates. Every place is the center from its own perspective. In the early decades of the 20th century, this realization had not yet taken hold. The prevailing view, even among many astronomers, was that the universe was static, infinite, eternal, and unchanging on the largest scales. The galaxies were thought to be scattered through space, much as stars are scattered through the sky, with no overarching motion to their arrangement. Yet the evidence was already building. Vesto Slipher, observing from Arizona, had measured the redshifts of spiral nebulae as early as the 1910s, finding most to be receding at great speeds. What they were, whether distant island universes or nearby clouds of gas, was still uncertain. The next step, the link between distance and speed, would come later, and with it the recognition that these spirals were galaxies far beyond our own, bound to the same expansion that began in the earliest moments of time. It is remarkable how the largest truths of the universe can remain hidden in plain sight, awaiting only the right combination of observation and interpretation. The galaxies, patient in their drift, had been expanding away from one another for billions of years before any human eye glimpsed the pattern. Only took the steady burning of the first stars to light up the expansion we would later measure. Only took the mergers of countless small galaxies to build the structures in which that light would shine. Only took the faint differences in density from the earliest moments to decide where galaxies would gather and where emptiness would persist. Yet there is still mystery here. The rate of expansion in these early times is set not just by the visible matter and radiation, but by the unseen mass of dark matter. Without it, galaxies would never have formed as quickly as they did. Dark matter's gravitational pull accelerates the clumping of matter, allowing structure to form even as space itself expands. Without it, the universe would be smooth still, its matter too diffuse to kindle the first starlight. The presence of dark matter adds weight to the paradox of expansion. The same invisible substance that draws matter together on small scales coexists with a universe that on the largest scales races apart. Gravity shapes. The local expansion shapes the global. The two do not cancel, but coexist each with its own domain. In the space between galaxy clusters, expansion stretches the voids larger and larger. These voids, great bubbles of almost nothing, make up most of the volume of the cosmos. The galaxies arranged in filaments and sheets are like dew on an unseen web tracing the edges of emptiness. The light from one side of a void to the other may take hundreds of millions of years to cross, and by the time it does, the void will have grown still larger. The galaxies, even in their drifting apart, are records of all this fossilized light, from stars that burned long ago, each spectrum a note in the larger harmony of expansion. They are not moving away because of some initial push, but because the stage on which they rest is still growing, and will grow for as long as the cosmos allows. It is here, in the slow separation of galaxies, that the expansion of the universe becomes more than an abstract measurement. It is a living process happening now, reshaping what the future sky will hold and what will fade beyond reach. The great distances will grow greater still, the familiar constellations will dissolve, and the visible universe will thin. But for now, the galaxies still shine together in the same sky, linked by the light that has crossed the spaces between them, light stretched and softened by the journey yet still arriving, still telling of a cosmos in quiet, steady motion. The hill above Pasadena is quiet in the early morning. The great dome of the telescope at Mount Wilson opens to the sky, revealing the cool air and the faint smell of pine. Below it the city is still, but here the night's work continues. Inside, Edwin Hubble adjusts the spectrograph, aiming at the faint smear of light from a distant galaxy. He's measuring not its brightness alone, but the position of the fine dark lines in its spectrum. Those lines are fingerprints, the unique signatures of elements like hydrogen and calcium, and in most galaxies they are shifted toward the red. Hubble knows that shift means the light's wavelength has been stretched. The larger the shift, the faster the galaxy must be receding. What is new in his work is the next step, comparing those speeds to the distances. Measuring distance in astronomy is not a simple matter. Even nearby stars require careful triangulation, the method called parallax, to gauge their true separation from Earth. For galaxies millions of light-years away, astronomers turn to brighter markers, like Cepheid variable stars whose steady pulsations reveal their luminosity. By comparing their true brightness to how faint they appear, Hubble can infer distance. When the numbers are plotted, the pattern is clear. The farther a galaxy is, the faster it recedes. This is not a scatter of motions in all directions. It is a smooth, linear relationship. Distance and velocity grow together, as if space itself were carrying the galaxies outward. The result, published in 1929, is a quiet revolution. The universe is not static, but expanding. The slope of Hubble's graph, the amount by which speed increases with distance, becomes a single number, the Hubble constant. Its units are awkward, a measure of velocity per unit of distance, but its meaning is profound. It is the rate at which the scale of the universe changes with time. The idea that the cosmos might be dynamic had already appeared in theory. Einstein's equations of general relativity allowed for an expanding or contracting universe, though he had at first rejected that possibility. To keep the universe static, he had introduced a cosmological constant, a term that counteracted gravity's pull. When Hubble's observations became known, Einstein is said to have called the constant his greatest blunder. Whether the phrase was truly his or not, the equations no longer needed that artificial balance. Expansion could be real. Yet the discovery also posed a subtle irony. The Hubble constant measures the present rate of expansion, but the very act of expansion means that rate can change over time. If the universe's matter and energy content evolve, so too does the slope of the distance-velocity relation. The constant is constant only in this moment. Hubble's initial value for the constant was far too large, making the implied age of the universe uncomfortably short, even younger than the Earth itself. Over the decades, better calibrations of distance have brought the number down, lengthening the cosmic timeline to billions of years. But the basic pattern remains untouched. Galaxies are not simply scattered in space. They are participants in a shared expansion. There is an elegance to the simplicity of the law. Choose any galaxy outside our local group, measure its redshift and brightness, and the relationship will place it somewhere along the same expanding curve. The slope of that curve is the Hubble constant, and in principle it links the observable present to the earliest moments of time. Only took a few decades of telescope technology to reveal what the cosmos had been doing for billions of years. Only took the faint stretched light of galaxies to overturn the idea of a static sky. Only took the patience to measure and compare to uncover the vast uniform motion in which everything participates. Yet the measurement is only as precise as the tools and methods allow. The distance ladder that leads to the Hubble constant is built from many rungs, each with its uncertainties: parallax for the nearer stars, Cepheids for nearby galaxies, type Ia supernovae for those farther still. Each step relies on the one below it, so any error can ripple upward into the final result. Even in the 21st century, the Hubble constant is still contested. One camp uses this ladder calibrated by local measurements to find a value near 73 km per second per megaparsec. Another camp uses the imprint of early universe physics from the cosmic microwave background, as measured by the Planck satellite, to infer a smaller number, about 67. The difference is not a mere rounding error. It is larger than the quoted uncertainties. This Hubble tension has become one of cosmology's most persistent puzzles. The tension might hint at new physics, perhaps a change in the behavior of dark energy over time, or an unknown component of the early cosmos, or it might be the result of subtle systematics in one or both methods. For now it remains unresolved, a quiet disagreement between the story told by the distant past and the one told by the nearby present. Still, the Hubble constant does more than measure expansion. It offers a way to estimate the size and age of the observable universe. In simple models, the inverse of the constant gives a rough timescale for how long the cosmos has been expanding, though the presence of dark energy complicates that calculation. Even so, the number captures something essential, the rate at which the very framework of space is changing beneath all motion. Hubble's own photographs captured on glass plates show galaxies as smudges against the darkness. They lack the colour and detail of modern images, yet they hold the same truth. Each smudge is a system of hundreds of billions of stars receding at a speed set not by its own will, but by the expansion of the cosmos itself. In that sense, the discovery is not about movement through space at all. It is about the growth of space, the increase of distance between objects that are not otherwise moving apart. Even now, the galaxies beyond our gravitational neighbourhood are being carried away, their light stretched ever longer, their presence growing fainter in the night sky. And so the hill above Pasadena, the quiet telescope dome, and the redshifted lines on a spectrograph plate mark a turning point in our understanding. The expansion rate of the universe is not a number buried in an equation. It is a rhythm slow and constant by which the stage of the cosmos changes size. It began in the first moments of time, and it continues still invisible to the eye, yet written into the light from every distant galaxy. To measure the expansion of the universe is to measure distance on a scale where familiar tools fail. No tape, no ruler, no laser beam can span the gulfs between galaxies. Astronomers build instead what they call the cosmic distance ladder, a set of linked methods, each step resting on the one below, extending farther and farther into the deep. The first rung is the most direct parallax. By observing a nearby star from 2 points in Earth's orbit 6 months apart, astronomers can detect a tiny shift in its apparent position against the background of more distant stars. The baseline is the diameter of Earth's orbit. The triangle it forms allows the distance to be calculated. Parallax works well for stars within a few thousand light years. Beyond that, the angles are too small to measure without extraordinary precision. The next rung turns to certain stars whose brightness varies in a regular pattern Cepheid variables. These stars swell and contract rhythmically, and their pulsation period is tightly linked to their true luminosity. Measure how fast they pulse, and you know how bright they really are. Compare that to how faint they appear, and the distance can be inferred. Cepheids bridge the gap between our own galaxy and its neighbours, reaching out to tens of millions of light years. Farther still, astronomers look for standard candles of another kind, type Ia supernovae. These are the explosions of white dwarf stars in binary systems triggered when they accrete enough mass from a companion to reach a critical limit. The physics of that limit ensures that the explosion always releases roughly the same amount of energy. Their peak brightness is immense, visible across billions of light years, making them excellent beacons for the far reaches of the cosmic web. Layer by layer, these methods build a coherent scale. Nearby stars set the calibration for Cepheids. Cepheids in turn calibrate the distances to galaxies that later host type Ia supernovae. With each step, the uncertainty grows, but so does the reach. The result is a ladder that climbs from the solar neighbourhood to the edges of the observable universe, tying together measurements of local motion and the grand expansion. It is a quiet irony that some of the most important cosmological numbers depend on the pulsations of single stars or the death throes of binary systems, phenomena entirely local in scale. Yet their role is to measure the behaviour of the universe as a whole. The ladder is not the only approach. For the earliest epochs, astronomers turned to the imprint of primordial physics, the cosmic microwave background, the ripples of baryon acoustic oscillations, the way galaxy clustering reflects the sound waves of the early plasma. These features set a scale in the very young universe that can be traced forward to the present, offering an indirect route to the expansion rate. But the ladder has a certain elegance. It moves step by step, each link in the chain anchored by direct observation, each distance rooted in the light of actual objects. It is this method that gives the higher value for the Hubble constant, the one that disagrees with the early universe estimates. That disagreement has been tested, rechecked, and refined, yet it remains. The process of measuring these distances is patient and exacting. For Cepheids, astronomers must observe through the dust of galaxies, correcting for absorption and reddening. For supernovae, they must capture the light curve, the rise and fall of brightness, with enough precision to fix the peak. Each data point is a small thing, a light curve here, a parallax shift there. But together they form a scaffolding for the whole edifice of cosmic measurement. Only took the alignment of Earth's orbit, and the careful recording of stellar positions to set the first rung. Only took the rhythmic breath of Cepheids to carry the measure beyond the Milky Way. Only took the rare and brilliant flash of a Type Ia supernova to illuminate the deep, and still each rung is imperfect. Dust metallicity and crowding in dense star fields can bias the Cepheid distances. The diversity of Type Ia supernovae is small but not zero, requiring corrections for subtle differences in their light curves. Even parallax, the most geometric of methods, must contend with the limits of instrument stability and calibration. Space telescopes like Hubble and Gaia have pushed these uncertainties down, sharpening the measurements, but they have not erased the tension. Instead, the improvements have made the disagreement with early universe predictions more robust. The two methods, the local ladder and the cosmic imprint, are now both so precise that their disagreement is statistically significant. In this there is a quiet mystery. If the tension is real, it could point to physics beyond the standard model of cosmology, perhaps an unknown form of energy in the early universe, or an interaction between dark matter and radiation, or something stranger still. If it is an artifact, it would mean that somewhere in the chain of measurement lies a systematic bias subtle enough to escape decades of scrutiny. The distance ladder is a reminder that in cosmology, the largest scales are measured by the smallest effects. A fraction of a degree in parallax, a few percent change in a light curve, a narrow absorption line in a galaxy's spectrum. These are the tools for gauging billions of light years. It is also a reminder that expansion is not uniform in every detail. Local motions can obscure the smooth flow like ripples on a slow current. Galaxies fall toward one another under gravity, superimposing peculiar velocities on the Hubble expansion. The ladder must reach far enough that these local motions average out, revealing the underlying trend. The farther we look, the fainter the markers become, and the longer their light has been stretched. Measuring them is like reconstructing a melody from notes heard across an immense echoing hall, each tone shifted lower and blurred by distance. The melody is still there, but it must be disentangled from the echoes. In this way, the distance ladder is both a practical tool and a poetic image, a structure rising from the earth, rung after rung into the open dark, built from the light of stars and the deaths of suns. It does not reach the edge of the universe, but it reaches far enough to tell us that the edge is not a wall, only a limit set by time beyond which light has not yet arrived. And at the top of that ladder the numbers speak of motion of galaxies carried a part of wavelengths stretched of a universe whose scale changes beneath every atom. The expansion rate is not just a fact of history, it is the quiet background to every moment, now a rhythm, that began with the first breath of space and continues still. Light has a way of telling stories without sound. When a beam from a distant galaxy arrives at a telescope's mirror, it carries within it a record of its journey, not in words, but in wavelength. The longer the path through expanding space, the more that wavelength has stretched. This is the language of redshift, a universal translation between distance, velocity, and time. In the simplest sense, redshift is a measure of how much the fabric of space has grown while the light was in transit. A photon leaving a galaxy billions of years ago may have started as blue light, but by the time it reaches us, it has been stretched into the red or even into the invisible infrared. The number assigned to this shift, denoted by z, grows with distance, and with the look-back time to when the light was emitted. Redshift is not the same as the Doppler effect in sound, though the analogy is tempting. In the Doppler shift, the motion of a source through space changes the frequency of the waves it emits. In cosmic redshift, it is not the galaxy moving away through space that stretches the light. It is the expansion of the space itself that does the work. The photon's crests are pulled farther apart because the very metric of the universe has changed in the time between emission and reception. Only took the patient splitting of starlight through a prism to reveal that every galaxy's spectrum is shifted. Only took the careful mapping of those shifts to see that the more distant the galaxy, the greater the change. Only took the recognition that this was not peculiar to our own vantage point, but true for all observers to conclude that expansion is a property of the cosmos itself. The redshift scale reaches from the smallest measurable values in nearby galaxies, barely stretched at all, to the extreme z values of 10 or more where the light was emitted when the universe was a small fraction of its current size. The most distant galaxies yet found their images captured by space telescopes staring for weeks into small patches of sky, are seen as they were just a few 100 million years after the Big Bang. Their photons have crossed almost the entire age of the universe to reach us, lengthening all the while. Redshift also allows astronomers to translate between distance and time. A galaxy at Zia Mahor 1 is not simply twice as far as one at Zia Mahor 5. The relationship is governed by the expansion history of the universe, which in turn depends on its contents, matter radiation, dark matter, and dark energy. To turn redshift into a true distance requires a model of cosmology. Change the model and the implied distances shift. This is both a strength and a subtle limitation. The same data, the same spectra of galaxies can be read differently depending on the assumptions. When the model matches reality, the distances and times inferred from redshift align perfectly with other measurements, such as the cosmic microwave background or baryon acoustic oscillations. When there is a mismatch, it can signal either new physics or an incomplete understanding. There is a quiet irony in how something so apparently simple a color shift in light encodes the most profound features of the cosmos. The position of a single spectral line can tell an astronomer how fast a galaxy is receding, how long its light has traveled, and how much the universe has grown in that time. Redshift is also the bridge between the present and the past. Observing a galaxy at Zeta Centauri 6 means seeing it as it was when the universe was less than 1 billion years old. The light we capture is ancient, but the act of observing it is immediate. The telescope's mirror reflects photons that have not interacted with matter since they left their source, their entire history written into their wavelength. Yet redshift is not only a tool for measuring the far away, it also reveals the subtle motions of the nearby. The Andromeda Galaxy, despite the general expansion, shows a blue shift, its light compressed towards shorter wavelengths, because its local gravitational pull toward the Milky Way overcomes the cosmic drift. On such small scales, peculiar velocities dominate over expansion. It is only when the distances grow large that the smooth trend of redshift takes over. In practice, measuring redshift requires careful attention. The lines in a galaxy's spectrum may be faint broadened by the motions of stars within it, or shifted by the dust that lies in the way. The calibration of the instruments, the stability of the detectors, the corrections for Earth's own motion, all these must be handled with precision. A tiny misplacement of a spectral line can translate into millions of light-years difference in inferred distance. Redshift also has its limits. At extreme distances, the light from early galaxies is shifted so far into the infrared that only specialized detectors can see it. Beyond a certain point, the first neutral hydrogen in the young universe absorbs much of the starlight, creating a dark age before reionization. In these cases, astronomers rely on other signatures like the shape of a galaxy's spectrum or the absence of light at certain wavelengths to estimate redshift indirectly. Still, it remains the most universal measure we have, one that applies equally to the glow of a distant quasar, the flicker of a supernova, or the diffuse hum of the cosmic microwave background itself. The last is redshifted not from visible light to red, but from the ultraviolet brilliance of a 3000-degree plasma down to microwaves at a temperature barely above absolute zero. Only took 13.8 billion years of expansion to turn that early glare into the faint hiss of the background radiation. Only took the stretching of space to carry galaxies from crowded neighborhoods into isolation. Only took the smallest shift in wavelength to map the largest structures in existence. When astronomers speak of the expansion rate, they are speaking in the language of redshift. It is the ruler by which distances are scaled, the clock by which look-back times are measured. Without it, the universe would be only a scattering of lights in the dark with no sense of motion, history, or scale. With it, the lights become markers along a path through time, each one fixed at a point in the cosmic past, each one telling how far the expansion has carried it from the others. The pattern they trace is the same from any vantage point, a quiet geometry in which there is no edge, no center, only the shared drift of everything through the growing fabric of space. And in every spectrum from the nearest galaxy to the most distant quasar, the same truth is written. The universe is not still. It breathes outward, carrying all light with it, stretching every wave until its origin is a memory embedded in color. In the vast arrangement of galaxies, there is a faint pattern so subtle that it is invisible to the eye, yet unmistakable in statistical maps. Galaxies are not placed at random. They follow a cosmic web with filaments, nodes, and great empty voids. And within this web is an ancient imprint, the frozen memory of sound waves that once rippled through the young universe's hot plasma. These are the baryon acoustic oscillations, or BO. In the first few 100,000 years before recombination, the universe was a dense fluid of photons, electrons, and baryons, the latter being protons and neutrons bound in atomic nuclei. In this fluid, gravity tried to draw matter together while radiation pressure pushed outward. The result was an oscillation, a slow pulsing of density like ripples spreading across a pond. These ripples had a characteristic size set by how far sound could travel in the plasma before recombination froze the pattern in place. When the universe cooled and neutral atoms formed, photons streamed freely away as the cosmic microwave background, but the matter retained the slight overdensities at specific separations. Over billions of years, these overdensities became more likely places for galaxies to form. Today, the imprint of BAO can be found by measuring the distribution of galaxies in enormous surveys. The Sloan Digital Sky Survey and others have mapped millions of galaxies, revealing that there is a slight excess of pairs separated by about 500 million light-years in today's units. That scale is the stretched relic of the original sound horizon, a standard ruler imprinted in the cosmos itself. Only took the first 380,000 years to set the size of that ruler. Only took the next 13 billion years to stretch it to its present measure. Only took the patient mapping of millions of galaxies to notice its presence at all. BAO is valuable because it is anchored in well-understood physics from the early universe. It is not subject to the same calibration uncertainties as the distance ladder. By comparing the observed BAO scale at different redshifts, astronomers can trace how the expansion rate has changed over time. The results provide a bridge between the early universe measurements of the cosmic microwave background and the late universe measurements from supernovae and Cepheids. And here too the Hubble tension appears. The BAO data, when combined with the cosmic microwave background, tend to agree with the lower value of the Hubble constant, the early universe number, rather than the higher value from the distance ladder. This agreement strengthens the possibility that the tension is not a simple error in the local measurements, but something deeper. The physics of BAO is simple in concept but subtle in detail. The sound waves travel at about half the speed of light in the plasma, their motion slowed by the inertia of baryonic matter. The competition between gravitational collapse and radiation pressure sets up a series of peaks and troughs in density. These are not sharp walls but gentle modulations barely perceptible in the early cosmos, yet amplified over eons into the patterns we can measure today. The very idea that sound waves once moved through the universe on scales of hundreds of thousands of light years is almost counterintuitive. There was no air, no atmosphere, only a plasma dense enough for photons to scatter constantly. In that medium, pressure could move matter just as vibrations can move air. When recombination occurred, the medium changed abruptly. The photons escaped and the ripples ceased to propagate. The moment was like a drum beat that stopped mid-resonance, leaving its final pattern frozen in place. It is a quiet irony that the universe's largest scale structure carries the signature of sound, though now it is utterly silent. The BAO pattern is not something we hear, but something we see in the distribution of galaxies. Each filament, each cluster, each void is part of the fossilized wavefronts of an ancient vibration. Measuring BAO requires more than a telescope. It requires a survey. Individual galaxies tell little on their own. The pattern emerges only from vast statistics where millions of positions are compared and their separations counted. The data are often displayed as a power spectrum, a graph showing how a structure varies with scale. The BAO feature appears as a small bump, a barely noticeable rise at the sound horizon scale. That small rise is enough to anchor our understanding of cosmic distances to remarkable precision. In modern cosmology, BAO is one of the three great pillars for measuring expansion, alongside the cosmic microwave background and the distance ladder. Each method approaches the problem from a different epoch, the CMB from the earliest observable light BAO from the time after galaxies began to form, and the ladder from the nearby universe. When all three agree, confidence in the model grows. When they diverge, the search for explanation begins. There is also a certain symmetry in how these methods link. The cosmic microwave background reveals the physics that sets the BAO scale. BAO then calibrates distances to intermediate redshifts. Those distances connect to supernovae and Cepheids in the local universe. It is a chain that runs from the first 380,000 years to the present, with expansion as the common thread. And yet BAO tells us more than just the rate of expansion. By comparing the scale of the pattern in the radial direction along our line of sight and the transverse direction across the sky, astronomers can probe both the Hubble parameter at different times and the angular diameter distance quantities sensitive to the nature of dark energy. This dual sensitivity makes BAO a tool not only for measuring how fast the universe is expanding, but also for exploring why that expansion is accelerating. Only took the first moments of cosmic history to encode this ruler into the matter distribution. Only took billions of years for galaxies to settle into its pattern. Only took the careful mapping of our era to reveal the silent echo. When we look at the large-scale structure, we're seeing not just the current arrangement of galaxies, but a record of the universe's earliest oscillations. The filaments and clusters are the peaks. The voids are the troughs. The distances between them tell of a time when light and matter moved together, and when the seeds of expansion's later story were being sown. The bow pattern will persist far into the future. Even as galaxies fade from view, the geometry they trace will remain a ghost of the early cosmos, measurable in principle long after individual stars have burned out. It is one of the most enduring clues we have to the history of expansion, a frozen wave on the largest possible sea. From the moment Hubble and his contemporaries recognized that the universe is expanding, there was an obvious question: how fast? The answer seemed to lie in one number, the Hubble constant h0, a single rate that could be measured, written down, and used to calculate the age and scale of the cosmos. Yet almost a century later, that number is still unsettled. The Hubble constant is conceptually simple. It is the velocity at which galaxies recede per unit of distance. Expressed in kilometers per second per megaparsec, it tells us that for every additional 3.26 million light-years a galaxy lies away, its recession speed increases by a certain amount. The principle is straightforward. The difficulty is in determining that certain amount with precision. The value of h0 is not merely academic, it is a parameter that permeates cosmology. It affects our estimate of the age of the universe, the size of the observable horizon, the density of matter, and the behavior of dark energy. It links the earliest light, the cosmic microwave background, with the present distribution of galaxies. A small change in h0 ripples through every other number in the standard cosmological model. Two main approaches dominate its measurement. One starts from the nearby universe, building the cosmic distance ladder, from parallax to Cepheids to supernovae, then reading off the slope of the recession-distance relationship. The other begins in the deep past, using the cosmic microwave background's detailed map of the early universe to infer today's expansion rate, assuming the standard model's physics holds from then until now. The irony is quiet but sharp. The two methods give answers that differ by more than the quoted uncertainties. The local ladder method produces a value around 73 km MPC. The early universe inference, as measured by the Planck satellite, gives about 67 km MPC. The difference is not large in everyday terms, but in cosmology, it is a chasm, a gap far too wide to dismiss as coincidence. Only took a century of refinement to bring the uncertainty on each method down to just a few percent. Only took that improvement to reveal that the two values do not converge. Only took the steady patience of observation to replace one mystery: is the universe expanding with another? Why do two correct methods disagree? The possibility that the tension is due to hidden systematic errors is not far-fetched. In the local method, small biases in calibrating Cepheid variables or accounting for dust could shift distances subtly. In the early universe method, assumptions about the composition of the cosmos, such as the exact behavior of neutrinos, could skew the extrapolation to the present. Both approaches have been tested repeatedly with independent teams, cross-checking each step. The tension remains. If both are correct, then the implication is profound. Our model of the universe is incomplete. Some proposals suggest that dark energy may not be constant, but may have evolved over time, altering the expansion history in ways the standard model does not allow. Others propose additional relativistic particles in the early cosmos, altering the sound horizon measured in the CMB. More speculative still are ideas about modified gravity or exotic interactions in the dark sector. The Hubble constant thus becomes more than a number, it becomes a potential doorway to new physics. History offers precedent. The discovery that the speed of light is constant led to relativity. The mismatch in Mercury's orbit led to the same. Sometimes the stubborn refusal of two measurements to agree is the sign of something fundamental waiting to be uncovered. There is a quiet irony in the word constant itself. In the standard cosmological model, the Hubble parameter changes with time. It is only h0, the value today, that is fixed. Billions of years ago, the expansion rate was far higher. In the far future, under the influence of dark energy, it will approach a different constant value, one tied to the vacuum energy density. The constant we argue over now is just the current frame in a much longer film. The methods used to measure h0 each have their own rhythm. The local ladder builds upward from the near and tangible, like climbing steps you can see. The CMB approach reaches backward, starting from the far and ancient, and works forward through theory. Both require extraordinary precision, the timing of a Cepheid's pulse, the calibration of a supernova's brightness, the mapping of the CMB's tiny temperature fluctuations. Each data point is a thread. Only when woven together do they form the cloth of the measurement. The disagreement between them has persisted long enough to earn its own name, the Hubble tension. It is discussed in conferences, papers, and hallway conversations. Proposed resolutions are tested and more often than not discarded. Each year new data arrive from space telescopes, ground-based surveys, and laboratory experiments. Each year the tension holds. Only took the invention of the telescope to discover the expansion. Only took the last few decades to measure it with precision. Only took that precision to find that our two best windows on the cosmos do not show quite the same scene. This uncertainty does not diminish the reality of expansion. The pattern of redshift with distance is secure, the broad history of cosmic growth unshaken. What it does is remind us that the universe still holds back some of its details, that even in an era of precision cosmology, the numbers can whisper of something we have yet to learn. In the meantime, h0 remains a living measurement, updated as new instruments come online. The James Webb Space Telescope refines distances to Cepheids in dusty galaxies. Radio arrays measure time delays in gravitationally lensed quasars, offering an independent local route to h0. Future surveys of BAO and the CMB will sharpen the early universe value. Somewhere in the cross-checks and overlaps the answer, whether agreement or true new physics will emerge. Until then, the Hubble constant sits at the heart of cosmology, a simple slope on a graph that stretches between now and the beginning of time, a number that ties together the earliest light and the farthest galaxies, and perhaps a clue to a deeper layer of reality than we yet know. The universe's expansion has never been steady. In the earliest fractions of a second during inflation, it was unimaginably rapid. In the first few billion years that followed it, slowed, tugged back by the mutual gravity of all matter and radiation. But in more recent cosmic history, something unexpected happened, the slowdown reversed. The expansion began to accelerate. The cause is assigned a name, dark energy, but the name is less an explanation than a placeholder. It refers to whatever is driving this acceleration, a form of energy that does not dilute as the universe grows, and whose effects overwhelm gravity on the larger scales. In the simplest models, dark energy is equivalent to Einstein's cosmological constant, uniform energy density inherent to the vacuum of space itself. Its discovery came in the late 1990s when two teams studying distant Type-A supernovae, the same standard candles used in the distance ladder, found that these explosions were fainter than expected for their redshift. The dimness meant they were farther away than they should be in a universe slowing under gravity alone. The only reasonable conclusion was that the expansion had been speeding up for billions of years, only took the faint flicker of exploding stars halfway across the cosmos to overturn the idea that gravity would always win. Only took the patient comparison of brightness and redshift to reveal that something unseen was pushing the galaxies apart faster and faster. Only took the recognition of this push to add a whole new chapter to cosmology. In the standard LCDM model, lambda cold dark matter dark energy is represented by L, the cosmological constant. Its strength is fixed, its nature simple in concept. As the universe expands, the density of matter drops, because the same amount of mass is spread over a larger volume. But the density of dark energy stays the same. Over time, matter's influence wanes, and dark energy's relative importance grows. Eventually it dominates and acceleration begins. The moment of transition happened roughly 5 billion years ago. Before that, the combined gravity of matter and dark matter was enough to slow the expansion, though never to reverse it. Afterward, the balance tipped. The effect is cumulative. The farther apart galaxies are, the more space there is for dark energy to act on, and the faster their recession becomes. It is a quiet irony that dark energy is both everywhere and almost undetectable, except by its effect on the universe as a whole. No laboratory has measured it directly. It does not clump like matter-form structures or emit light. Its signature is only visible in the geometry of space-time itself, in the way distant objects appear fainter, or in the way large-scale structure evolves over time. Other models try to go beyond the cosmological constant. Some suggest a quintessence field that changes over time, altering the rate of acceleration. Others explore modifications to general relativity, in which gravity itself behaves differently at cosmic scales. There are even scenarios in which dark energy might one day reverse signs, slowing the expansion again, or collapsing the cosmos entirely. At present, observations are consistent with L being constant, but the data still leave room for more complex possibilities. Dark energy also deepens the mystery of the Hubble tension. The early universe value of H0 depends on the size of the sound horizon at recombination, which in turn depends on the expansion history before that time. If dark energy's behavior has changed since then, it could shift the inferred rate today. This is one reason why precision measurements of the expansion at intermediate redshifts halfway back in time are so important. In maps of the cosmic web, the influence of dark energy is not visible in the positions of galaxies, but in the way those positions evolve with time. Surveys like the Dark Energy Survey DES and the upcoming Euclid mission are designed to trace this evolution using weak gravitational lensing and BAO to see how structure grows under the combined influence of matter's pull and dark energy's push. The effect on the future is profound. If dark energy is indeed a cosmological constant, the acceleration will continue forever. Galaxies not bound to ours by gravity will eventually slip beyond our observable horizon. Their light will be stretched to invisibility. Their presence will fade from any possible observation. The night sky billions of years from now will contain only the remnants of our local group set against an empty dark. Only took 5 billion years for dark energy to become the dominant force in cosmic expansion. Only took a few decades of precise observation to detect its presence. Only took a name dark energy to remind us how little we truly know of what it is. There is restrained elegance to how dark energy fits into the equations of cosmology. In Einstein's field equations, it acts like a pressure with a negative value driving space-time to curve outward instead of inward. This curvature is not a distortion on a surface we can see, but a global change in the geometry of the universe itself. Distances grow faster than they would under gravity alone, and the growth accelerates with time. In the far future, if L is constant, the expansion rate will approach a fixed value, set by the dark energy density. Galaxies beyond a certain distance will recede faster than light relative to us, not in violation of relativity, but because space itself is expanding. Their light will never reach us, and they will pass into a region of space-time forever causally disconnected from ours. This scenario is often called heat death. not because it ends in fire, but because it ends in uniformity. As galaxies vanish from view and stars burn out, the cosmos will become cold, dilute and quiet. The expansion will continue, but with nothing left to change, it will be motion without consequence. It is possible that the true nature of dark energy will be stranger still. Perhaps it is not constant. Perhaps it will grow stronger, leading to a big rip in which even galaxies, stars and atoms are torn apart. Or perhaps it will decay into something else, changing the fate of the universe entirely. For now, these remain speculations bounded only by the requirement that they match the observations we have so far. Dark energy's discovery was not the end of the story of expansion, but the beginning of a deeper mystery. It tells us that the universe is not simply coasting outward from its origin, but is under the influence of a force that grows in significance with time. It reminds us that cosmic history has chapters still to be written, shaped by something that fills all of space, yet reveals itself only through the geometry of the whole. As acceleration continues, the universe becomes a place where the distant is not merely far but unreachable. With every passing billion years, more galaxies slip beyond a horizon that is not a physical edge, but a boundary set by light's finite speed and the relentless growth of space. This is the cosmic event horizon, the dividing line between what can still send light to us and what has already been carried away too quickly for its light ever to arrive. The existence of such a horizon is a direct consequence of dark energy's dominance. In a decelerating universe, even if expansion continued forever, the observable region would grow without limit, and light from ever more distant places would eventually arrive. But in an accelerating cosmos there is a limit. Beyond a certain point now, about 16 billion light-years away in proper distance, any signal emitted today will never reach us. The space between will expand faster than the signal can close it. Only took the steady, silent push of dark energy to place an ultimate cap on the reach of our observations. Only took the constancy of light speed to set that cap in stone. Only took the patient unfolding of billions of years to begin carrying galaxies beyond it. The irony is that many of these galaxies are still visible now, because the light we see left them billions of years ago when they were closer. But as time goes on, fewer will remain in view. The most distant will fade first, their light stretched into wavelengths too long for any conceivable detector. Eventually, even galaxies currently within the horizon will drift beyond it. The sky will thin not by destruction but by separation. In the deep future, our descendants, if any, will inherit a cosmos that seems far smaller than ours. The Milky Way, Andromeda, and a few dozen dwarf galaxies in our local group will merge into a single massive elliptical. Beyond that, there will be nothing visible, no other galaxies, no cosmic microwave background, no evidence of expansion at all. The universe will appear static, timeless and empty, much as astronomers once believed before the 20th century. This scenario is a quiet reminder that cosmology itself is a product of timing. We live in a rare epoch when the evidence for expansion is abundant galaxies everywhere. The background glow still bright enough to detect the BAO pattern, still measurable across vast surveys. Future observers in an isolated galaxy will lack these clues. Without them, the idea of an expanding universe will be far harder to discover, perhaps impossible. There is also a horizon in time, the look-back limit set by the cosmic microwave background. No matter how powerful our telescopes become, we will never see farther in light than 380,000 years after the Big Bang. The opaque plasma of earlier times hides anything before recombination from view. Gravitational waves might offer a way to pierce that veil, but in electromagnetic light the horizon is permanent. The two horizons in space and in time shape the boundaries of what cosmology can know. They're not obstacles that can be overcome with better technology. They're built into the geometry of the universe itself. They define not just what we see, but the totality of what is visible from any point in space-time. Only took the finite speed of light to ensure that every observer has their own private observable universe. Only took the growth of space to make those universes shrink in content over time. Only took the brief overlap of our current epoch with the cosmic past to give us the view we have now. The cosmic event horizon is not like the event horizon of a black hole, though the analogy is tempting. For a black hole, crossing the horizon means falling irreversibly toward a singularity. For the cosmic horizon, crossing means simply becoming forever out of causal contact. The galaxies that drift beyond it will go on evolving, forming stars, perhaps even life. But they will do so in a region of the universe forever disconnected from ours. There is a soft irony in the thought that most of the universe's galaxies are already beyond our event horizon. Of the hundreds of billions we can currently see, the majority are so far away that no light they emit now will ever reach us. We see them only as they were in the past, their present and future beyond our knowing. In a sense, the expansion has already written them out of our shared story. They are participants in the same cosmic evolution shaped by the same physics, but their subsequent chapters will unfold in a book we cannot read. The shrinking of the observable universe does not mean the cosmos itself is contracting, quite the opposite. The total volume of space is increasing faster than ever. It is our access to that volume that is contracting our window onto the whole narrowing as acceleration takes over. Astronomers can predict the pace of this change with some confidence. In about 100 billion years, any galaxies outside our local group will be gone from view. In trillions of years, even the faint glow of the cosmic microwave background will be stretched into radio waves so long they will be effectively undetectable. The universe will be dark not because light no longer exists, but because it has been carried to wavelengths and intensities beyond the reach of any receiver. In that far future, physics itself will not change, but the evidence for its grandest scales will have vanished. The geometry of expansion will still shape space-time, but there will be no accessible proof. The cosmic history we reconstruct today will be unknowable to any astronomers then. This fleeting accessibility of the cosmic past makes our current age extraordinary. We are at once late enough in cosmic history for the first galaxies to be mature and bright, and early enough that most of the universe is still within sight. It is a balance that will not last. Only took a few decades of modern astronomy to recognize the expansion. Only took a century to begin measuring its rate with precision. Only took the emergence of dark energy to show that this view of the cosmos is temporary. The event horizon is not a thing we can reach or cross because it moves with time always at the edge of the possible. It is defined not by distance now, but by what light can do in the future. It is the sum of all paths that never quite arrive, all signals that forever fall short. And so the accelerating universe is a place where the largest truths are visible only briefly, where the map of the whole is available for a limited time. We happen to live in that time, a fact as accidental as the position of a galaxy in a filament, or the presence of a planet around a star. The view we have now is not the universe as it will always be, but the universe in this moment caught between the openness of its youth and the solitude of its far future. Over billions of years, the acceleration reshapes not just what is visible, but what is possible. Every second that passes increases the number of galaxies receding faster than light from our perspective. They are not breaking the speed limit set by relativity. No object moves through its local space faster than light, but the metric of space itself is changing in such a way that the distance between us and them grows faster than any photon can close. This distinction, subtle as it is central to understanding the expansion. Relativity sets a speed limit for motion through space, but not for the growth of space itself. The expansion stretches the wavelength of every photon and the separation between every unbound object, and it does so without resistance. From the standpoint of the galaxies themselves, nothing unusual is happening. They are simply stationary in their own frames, surrounded by space that lengthens in all directions. Only took the translation of redshift into recession velocity to reveal that some galaxies are already beyond this threshold. Only took the patient accumulation of data to map where that limit lies today. Only took the recognition of this superluminal recession to understand that much of the universe is already lost to future communication. Within our own gravitationally bound region, the local group, the story is different. Gravity overpowers the feeble push of dark energy here, keeping the Milky Way Andromeda and their satellite galaxies tied together. In about 4 billion years, the Milky Way and Andromeda will merge their stars, settling into a new, larger elliptical system. Dwarf galaxies will be absorbed. Their orbits will decay. In time, the local group will become a single massive island in a widening cosmic sea. Outside that island, the flow of expansion is inexorable. Galaxy clusters that are now near enough to be seen in exquisite detail will fade as their light is stretched to longer and longer wavelengths. Clusters farther still, the Virgo cluster. The Coma cluster will vanish from view entirely, their present-day brilliance preserved only in ancient photons still en route to us. There is an irony in the fact that we observe the universe during one of its most connected eras. The great walls and filaments of galaxies that we now map with precision will dissolve into invisibility not because they have fallen apart, but because they have passed beyond the reach of any light we could send or receive. The cosmic web itself will remain in some form, but our view of it will collapse inward until only the local strand remains. This shrinking of the accessible universe changes the meaning of now in cosmology. In everyday life, now is a thin slice of time shared across a few meters or kilometers. In the cosmos, now is a jagged surface across space-time connected by the path of light. We do not see galaxies as they are, but as they were when their light began its journey. As acceleration carries them farther away, that journey lengthens and then now slips further into their past. Eventually there comes a point where no future light can bridge the gap where their now will never reach ours. This is why the event horizon is a boundary not only in space but in time. It divides the history of the universe into regions that can still interact and those that cannot. Beyond it, events may unfold, but they will be causally disconnected from anything within our reach. Even the most powerful signal's gamma-ray bursts gravitational waves cannot cross it, once expansion outpaces them. Only took a finite speed of light to set this limit. Only took the steady accumulation of dark energy's influence to make that limit permanent. Only took the flow of cosmic time to move more and more of the universe past it. It is worth noting that expansion does not pull everything apart. On small enough scales where gravity or other forces are strong, the metric expansion of space has no measurable effect. Atoms, planets, solar systems, and galaxies remain bound. The space between the Earth and the Moon is not expanding. The solar system does not slowly stretch under dark energy's influence. These structures are too small and too strongly held together for the cosmic drift to touch them. But at the scales between galaxy clusters, expansion reigns. The voids grow, the distances widen, and the connections between superclusters weaken. Even without dark energy, the universe would expand forever under the influence of its initial momentum, though ever more slowly. Dark energy transforms that gentle drift into an accelerating separation, turning the possible reunions of the far future into permanent goodbyes. In the LCDM model, the mathematics of this acceleration is simple. The scale factor at t grows exponentially with time when dark energy dominates. The recession velocities of distant galaxies therefore increase in proportion to their distance, leading to the linear Hubble relation we see today, and beyond a certain distance to superluminal recession. This exponential growth ensures that the event horizon remains finite, even as the total universe is infinite. The paradox is that in this infinite universe, each observer's visible domain is finite and shrinking in content. Two galaxies separated by more than twice the event horizon distance today can never exchange a signal, no matter how long the universe lasts. They are part of the same universe in principle, but not in practice. From a human perspective, this is less a cause for alarm than for contemplation. The galaxies beyond our reach were never going to influence our lives, but from a cosmological perspective, it is the slow erasure of the observable record. The data we can gather today across billions of light years is the fullest it will ever be. The map will only grow emptier. Only took the merging of nearby galaxies to guarantee the survival of a handful of cosmic neighbours. Only took the faint persistence of their starlight to keep the sky from going completely dark in the unimaginably distant future. Only took the accident of our era for us to be able to measure the Hubble constant map BAO and detect the cosmic microwave background. In the farthest times we can imagine, expansion will be less a subject of observation than of inference, if there is anyone left to infer it. With no external galaxies to serve as markers, the expansion will leave no visible trace. The universe will appear static and changeless, as it did to astronomers of the ancient past. The difference will be that this appearance will then be true, at least for all practical purposes, within the surviving island of bound matter. The accelerating universe thus writes a strange ending for the story of cosmology. The field thrives now because the evidence is abundant. It will wither in the future because the evidence will be gone. The expansion will continue, but the knowledge of it will not. In this sense, the universe is not just expanding, it is also slowly hiding itself from view. When astronomers speak of mapping the universe, they do not mean drawing its borders, for it has none, but charting the geometry of space-time itself. Expansion is not simply a matter of things moving apart. It is the changing of that geometry, the way distance is defined between any 2 points. In an expanding universe, the concept of center loses meaning. Every galaxy sees every other galaxy moving away, with velocities proportional to their distances. There is no special location from which expansion originates. The pattern looks the same everywhere. The balloon analogy, though imperfect, is the most common way to visualize it. Galaxies like dots on the surface, all receding from each other as the surface stretches. The balloon has no edge from the perspective of the dots, and no dot sits at the center of its two-dimensional surface. Only took the realization of homogeneity and isotropy to understand that this symmetry is a property of the whole, not a coincidence of our vantage. Only took the combination of relativity's equations with astronomical surveys to see that the universe is the same on average in all directions. Only took the absence of any center to confirm that expansion is a feature of space itself, not motion through some surrounding emptiness. In this geometry, the distance between 2 points depends on how it is measured. Comoving distance, proper distance, luminosity distance each, is defined for a different purpose, and each changes differently with time. For light, the relevant measure is the path it traces through the expanding metric. This is why an object we say is 10 billion light-years away may have been much closer when the light was emitted and much farther by the time it arrives. One of the most counterintuitive features of cosmology is that the observable universe is larger than its age in light-years might suggest. Because space has been expanding while light travels, the most distant galaxies we can see now lie about 46 billion light-years away, even though the universe is only 13.8 billion years old. The expansion has carried them far beyond the simple distance implied by time multiplied by the speed of light. The lack of an edge does not mean the universe must be infinite. Its curvature, the way straight lines behave over large distances, determines whether it is finite or infinite in extent. Observations of the cosmic microwave background show that space is very nearly flat, with any curvature too small to measure at current precision. A perfectly flat universe can be infinite, or it can be finite if it wraps back on itself in higher dimensions. The distinction remains an open question. The large-scale structure of the cosmos mapped in detail by galaxy surveys resembles a cosmic foam. Filaments of galaxies span hundreds of millions of light-years, intersecting in clusters where the density is highest. Between them lie enormous voids, regions almost empty of matter. This web is the evolved form of the tiny density fluctuations seen in the cosmic microwave background, amplified by gravity over billions of years. Expansion shapes this web not by altering the pattern of matter within bound structures, but by stretching the space between them. Filaments lengthen, voids widen, clusters drift apart. The pattern remains, but its scale increases. In this way, the geometry of the universe is not fixed, but dynamic, a stage whose dimensions change as the play unfolds. Only took the mapping of millions of galaxies to see this geometry clearly. Only took the statistical tools of correlation functions and power spectra to measure its scale. Only took the translation of those scales into comoving units to reveal how expansion has altered them over time. General relativity provides the framework for describing this geometry. The Friedmann-Lemaitre-Robertson-Walker FLRW metric derived from Einstein's equations encodes the assumptions of homogeneity and isotropy. The metric's scale factor HT is the single function that determines how distances change with cosmic time. The Hubble parameter HT is the rate of change of that scale factor divided by the scale factor itself. HT decreases when matter dominates, increases when dark energy dominates, and is tied directly to the density and pressure of all components of the universe. In this framework, expansion is not an explosion, but a smooth, continuous change of scale. There is no outside into which space expands and no inside from which it emerges. Every point moves away from every other point, not because of motion through a pre-existing void, but because the distances themselves are increasing. The elegance of the FLRW model lies in how much it explains with so few parameters: the Hubble constant, the matter density, the dark energy density, and the curvature. With these, the entire history and fate of the expansion can be modelled. And yet within this elegance lie the open questions why the densities have the values they do, why dark energy behaves as it does, and whether the early universe inflation was a one-time event or part of something larger. The geometry of the universe also governs the paths of light and matter. Massive objects curve space-time, bending the trajectories of photons in a process known as gravitational lensing. On small scales, lensing creates arcs and multiple images of background galaxies. On large scales, it subtly distorts the apparent shapes of galaxies across the sky, an effect called weak lensing. These distortions carry information about the distribution of matter and the growth of structure, and thus about the expansion rate itself. The connection between geometry and expansion runs deep. In a closed universe with positive curvature, expansion could eventually halt and reverse, leading to a collapse. In an open or flat universe with enough dark energy, expansion continues forever, accelerating toward emptiness. The current data indicate a flat geometry, with ongoing acceleration consistent with the cosmological constant model. Only took the measurement of the first few acoustic peaks in the CMB to determine the curvature to within a fraction of a percent. Only took the combination of that measurement with galaxy surveys to confirm the large-scale flatness. Only took the refinement of these methods to reduce one of the biggest uncertainties in cosmology, to one of its smallest. Still, flatness raises its own puzzles. The early universe had to be tuned with extraordinary precision for the curvature to be so close to zero today. Inflation provides one possible explanation, stretching any initial curvature toward flatness, much as blowing up a balloon makes a small patch of its surface seem flat to an ant walking across it. The global geometry, the local curvature around massive objects, and the dynamic scale of space are all facets of the same reality. The universe is a fabric, not a static backdrop. Its shape and size evolve, its distances change, its horizons shift. We are part of that fabric, moving with it, unable to stand outside and watch it grow. And in that movement, expansion is not just a change of place, but a change of possibility, defining what can be seen, what can be reached, and what will eventually be lost to the widening of the whole. If expansion is the stage on which cosmic history unfolds, then the question of fate is the script's final act. The geometry, contents, and energy of the universe together determine how that act will play out, shaping whether space continues to grow forever, halts, or reverses. For most of the 20th century, this was a central question in cosmology. Would the universe end in a big crunch, a big freeze, or something else entirely? In a universe dominated by matter alone, the outcome would hinge on its density. If the average density were greater than a certain critical value, gravity would eventually slow the expansion to a stop and reverse it, leading to a collapse. If the density were exactly at the critical value, expansion would continue forever, but slow asymptotically towards zero. If the density were less, the universe would expand forever, but always at a decreasing rate. For decades, observations of galaxies, galaxy clusters, and large-scale structure suggested that the universe's matter density, including dark matter, was below the critical threshold. This hinted at a future of eternal expansion, but the discovery of cosmic acceleration in the 1990s changed the question entirely. Now the fate of the universe was tied not to matter alone but to dark energy. Only took the dimming of a few dozen distant supernovae to shift the entire debate. Only took the recognition that acceleration, not deceleration, was underway to realize that matter's gravitational pull was no longer the decisive factor. Only took the insertion of dark energy into the equations to rewrite the universe's ending. If dark energy is a cosmological constant expansion, will not just continue forever, it will accelerate without end. Over time, the observable universe will empty as more and more galaxies pass beyond the event horizon. Star formation will slow as galaxies exhaust their gas. The night sky will darken, constellations will vanish, and only the remnants of our local group will remain bound together. Eventually, after trillions of years, even those stars will burn out, leaving cold remnants orbiting in darkness. This scenario is often called the heat death or big freeze, a universe asymptotically approaching uniform temperature and maximum entropy. If dark energy is not constant, the possibilities multiply. A form of dark energy that grows stronger with time, with an equation of state parameter less than 1, could lead to a big rip. In this extreme acceleration would eventually overcome all forces tearing apart galaxy clusters, then galaxies, then stars, and finally atoms themselves. The scale factor would diverge to infinity in a finite time, ending the cosmos in a burst of infinite expansion rate. Conversely, if dark energy decays over time, its influence could diminish enough for gravity to regain dominance. Expansion could slow, halt, and reverse, leading to a big crunch. In that case, the universe would collapse back into a dense hot state, perhaps triggering another round of expansion, as some cyclic models propose. There are also speculative scenarios where the end is neither heat death nor collapse. In some models, quantum fluctuations could cause regions of space to tunnel into different vacuum states, altering the constants of nature. If such a transition occurred in our observable universe, It could expand at nearly the speed of light, rewriting the physical laws as it went. From within, the change would arrive without warning, replacing everything in an instant. The uncertainty about fate mirrors the uncertainty about origin. We can model the first seconds after the Big Bang with great confidence, but the moment before, if before is even a meaningful term, remains hidden. Likewise, we can project the expansion billions or trillions of years into the future, but the farthest horizon depends entirely on the nature of dark energy, which is still unknown. Only took a cosmological constant to make infinity the likely outcome. Only took a change in that constant's behaviour to open the door to endings more violent or more sudden. Only took the presence of a single mysterious term in Einstein's equations to turn prediction into speculation. In any of these futures, the role of expansion is central. It determines not just the scale of the universe, but the sequence in which cosmic structures fade from relevance. Galaxy clusters dissolve, first followed by galaxies followed by the systems within them. The final survivors of heat death would be isolated particles and black holes. Even black holes would not last forever over unimaginably long timescales. They would evaporate via Hawking radiation, releasing their mass as faint cold light. In the Big Rip scenario, these sequences are accelerated. Galaxy clusters might dissolve millions of years before the end stars, mere minutes before planets and atoms in the final instance. The difference between trillions of years and seconds is only a matter of dark energy's behaviour. The cosmic microwave background offers a reminder of how much can change in cosmic time. When it was released, the universe was 3,000 kelvins and opaque. Now it is 2.7 kelvins and transparent, with structures billions of light-years in size. In the far future, any surviving observers would see a universe transformed beyond recognition, its background radiation stretched to wavelengths larger than the observable horizon, its structure erased by acceleration. In all these scenarios, expansion is both creator and eraser. It gave rise to the space in which galaxies formed, and it will eventually carry them beyond each other's reach. It is not a force in the traditional sense, but the ongoing consequence of the universe's initial conditions and its contents. Its presence in the equations of cosmology is inevitable. Its details remain a map we are still drawing. The fate of the universe is not a question with an answer waiting in the near term. It is a trajectory that will play out over scales of time so large that human history, even planetary history, is a blink. The significance of our moment is not that we stand at the end, but that we stand at a rare vantage point, able to look far back and far ahead before the view begins to close. Only took the accident of living in this brief window of cosmic time to make the question of fate an observational science. Only took the convergence of instruments theory and data to give us enough certainty to see the broad outlines. Only took the persistence of unanswered questions to keep those outlines blurred at the edges. And so the expansion rate of the universe is more than a parameter to be measured. It is the thread that connects its beginning to its possible endings. Whether the story stretches to infinity, loops back on itself, or ends abruptly, the expansion is the through line, the quiet background motion that shapes everything else. Even as cosmology projects the fate of the universe, trillions of years ahead, it also turns its attention to the expansion here and now, not in the abstract, but in the slow drift of our own galactic neighbourhood. For all the immensity of cosmic acceleration, the local universe is shaped most strongly by gravity, and the interplay between local binding and global expansion reveals how these two regimes coexist. The Milky Way is not a solitary wanderer. It is part of the local group, a gravitationally bound collection of more than 50 galaxies, most of them small dwarfs. The largest members are the Milky Way and Andromeda, with the Triangulum galaxy a distant third. Despite the overall expansion of the universe, these galaxies are not receding from each other. Andromeda, in fact, is approaching us at about 110 kilometers per second. This is not a contradiction of Hubble's law, but an example of its limits on scales smaller than a few megaparsecs. Local gravitational interactions can outweigh the gentle pull of expansion. Only took the first measurements of Andromeda's blue shift to show that cosmic expansion is not universal at every scale. Only took the realization that bound systems are effectively immune to the metric growth of space. Only took the patient mapping of our surroundings to see where gravity wins and where expansion takes over. The local group's eventual merger into a single giant elliptical galaxy will mark the end of our direct connection to the broader cosmic web. In perhaps 4 to 5 billion years, the Milky Way and Andromeda will collide, their spiral arms shredded, their stars flung into new orbits. While such mergers can trigger bursts of star formation, by then the supply of cold gas may be too depleted for much renewal. The result will likely be a vast reddish galaxy, filled mostly with aging stars. Beyond the local group lies the Virgo supercluster, of which we are a part. Virgo itself is about 54 million light-years away, a gravitationally bound cluster with thousands of galaxies. In the absence of dark energy regions like Virgo might eventually merge with others, forming ever larger structures. But acceleration changes this story. The supercluster is not bound in its entirety. The outer regions are already receding too quickly for gravity to pull them in. In the far future, only the densest cores of such structures will resist the flow of expansion. The scale at which expansion overtakes gravity is called the turnaround radius. For the local group, that radius is only a few million light-years. For the Virgo cluster, it is a few tens of millions. Anything beyond it is effectively adrift on the expanding fabric of space, destined to drift farther with time. From our current vantage, we can map the nearby universe with extraordinary precision. Redshift surveys trace the flow of galaxies out to hundreds of millions of light-years, revealing patterns of inflow toward massive clusters and outflow from great voids. These maps are snapshots of a dynamic process, the slow growth of large-scale structure and its eventual freezing as acceleration halts the collapse of all but the most overdense regions. Only took the careful combination of distance measurements and redshift maps to see these flows in 3 dimensions. Only took the use of peculiar velocities to distinguish local motion from the global expansion. Only took decades of survey work to build a complete picture of our place in the web. The influence of expansion on local motion is subtle. For the Earth orbiting the Sun at 30 kilometers per second, the metric growth of space between here and the Moon is negligible, far too small to detect with current instruments. Even at the scale of the solar system's edge, the expansion is utterly overwhelmed by the Sun's gravity. It is only when we reach the intergalactic realm that the effect becomes noticeable, and only beyond the bounds of the local group that it dominates. This coexistence of the bound and the unbound is one of the quiet ironies of cosmic expansion. The same equations that describe the growth of the largest voids also permit the stability of planets around stars. Space can stretch between galaxy clusters without stretching the bonds that hold atoms together. Expansion acts on the scale of the universe as a whole, while the smaller scales remain anchored by their own forces. The same principle applies in reverse. While galaxies within a cluster remain bound, the cluster as a whole may be receding from another cluster across a supercluster scale void. The cosmic web is not a rigid net, but a set of knots drifting apart, their threads slowly lengthening. The expansion rate, the Hubble parameter, at any given time sets the pace for this drift, but gravity shapes the exceptions. In the present epoch, dark energy's influence has begun to halt the growth of new, large-scale structures. Simulations show that while smaller bound objects like galaxies and clusters will continue to merge for some time, the formation of new superclusters will slow and eventually stop. The cosmic web, so intricate and dynamic today, will freeze into a more static arrangement in the distant future. The view from Earth is therefore unique in cosmic history. We see the web in mid-growth, its filaments still feeding galaxies with cold gas, its void still expanding, its clusters still accreting matter from their surroundings. Billions of years from now, the filaments will have thinned their gas, depleted their galaxies, isolated. Expansion will have locked the structure in place like a photograph taken in motion and then paused forever. Only took the accident of observing now to capture the web in this transitional phase. Only took the interplay of expansion and gravity to set the scale at which change slows. Only took the rise of dark energy to make this freeze inevitable. The local group's merger will be the last grand act of cosmic architecture visible from our position. Once it settles, the new galaxy, sometimes called Milkomeda, in speculative writing will drift in solitude. Its stars will still trace the same physical laws, but its night sky will no longer hold the external markers of expansion. Without those markers, the story of the cosmos will be harder to reconstruct, its history harder to guess. From the perspective of a civilization in that far future, the universe will seem quiet, ancient and unchanging. The great truth of expansion will still be embedded in the laws of physics, but it will no longer be obvious in the sky. The knowledge we have today will be one of the many things that can only be passed on or lost. In that sense, our measurements of the expansion rate are not just scientific milestones, they are records for the future. They capture a moment in the universe's life that will never come again, a moment when the galaxies still speak to each other in light, when the cosmic microwave background still glows, when the geometry of space is still written plainly in the distribution of matter. The vastness of the cosmos is not empty of pattern. Expansion stretches space itself, but it also preserves within its flow the faint traces of its earliest conditions, the delicate patterns left by primordial physics. These patterns weave through the distribution of galaxies, the background radiation, and even the abundance of elements. Together they tell the quiet story of how the universe grew from simplicity into complexity. As the expansion carries galaxies ever farther apart, it also acts as a metronome marking the passage of cosmic time. The rate at which space stretches dictates the age of the universe, the distances light must travel, and the very possibility of structures forming. It is the pulse underlying all motion, silent yet inexorable. Only took a single number, the Hubble constant, to tie these threads together, connecting the present moment to the moment of creation. Only took patient measurements of light time and distance to turn this number from a curiosity into the foundation of modern cosmology. Only took the courage to ask hard questions about the nature of dark energy, dark matter, and the shape of space to open the path forward. Yet the story is not complete. Mysteries remain. Why is the expansion accelerating? What is dark energy? Why does the Hubble constant differ depending on how we measure it? These questions mark the frontier of knowledge, the horizon toward which inquiry continues to move. The expansion rate is not simply a datum but a lens. Through it we glimpse the hidden components of the cosmos. Through it we confront the limits of observation and the bounds of theory. Through it we touch the vastness of time and space, the interplay of forces and the emergence of order. And yet expansion is also a quiet surrender. It tells us that the universe is not fixed, not static, not eternal in a single form. It flows, it grows, it changes, and in doing so it creates horizons beyond which we cannot see boundaries, we cannot cross futures, we can only imagine. The galaxies, the background, light, the cosmic web all drift in the current of expanding space, carried by a force that was born in the first breath of time and will shape the fate of all that is. Only took a moment after the Big Bang for space to begin stretching. only took the slow unfolding of billions of years for that stretch to shape everything we know, only took our presence brief and small to witness, measure, and wonder at this quiet motion. The expansion rate of the universe is the rhythm of cosmic time, a silent music played on the fabric of reality. It is the breath of creation, the pulse of infinity, the background against which all existence moves. And as space continues to stretch, carrying light matter and time itself, the universe whispers its secret, that nothing stands still, that all is flowing, that every moment is a step in the endless unfolding of the whole.